A cantilever timber beam with a span L equal to 3.6 meters support a linearly distributed load, that is a uniformly varying load. Maximum value of the intensity equal to W0. The beam has a width is equal to 240 mm and the height is equal to 180. Allowable maximum value of the bending stress in the wood is 7.6. So sigma B maximum is known 7.6. Calculate the magnitude of the maximum load W0, that is intensity we have to find out. So dimensions of the section is width equal to 240, height is equal to 180, maximum bending stress is given as 7.6 and we have length equal to 3.6. Value of W0 you have to find out. Axes of symmetry are horizontal and vertical and the intersection of the two axes of symmetry is same as our centroid G. Horizontal axis here is a Z axis and the vertical axis is Y axis. The distance of a top fiber and bottom fiber is same is equal to C. So both the fiber here, top fiber or bottom fiber, they are equidistant. So value of C you have to take as h by 2. H by 2 is same as 180 divided by 2, that equal to 90 mm. Moment of inertia is bh cube by 12. So we can calculate here what is the maximum bending moment. It can be subjected. By flexure formula, we have maximum value of a bending stress is same as the maximum value of bending moment M max multiplied by C divided by I. So maximum value of a bending moment M max is same as sigma B max. Sigma B maximum is 7.6 multiplied by I. I is BD cube by 12. We have B is equal to 240. H cube is 180 cube and is divided by 12 and again divided by C, that equal to 90. So maximum value of a bending moment will come out to be 9.849 into 10 to the power 6, that will be Newton mm. Dividing by 10 to the power 6, we will get a maximum bending moment is 9.849 will be kilonewton meter. Now we have to find out where the maximum bending moment will occur in the case of uniformly distributed load. Naturally, the maximum bending moment will occur at a support, that is at point A. For this purpose, we will convert UVL into point load. Since we have a triangle here, so equivalent load will be the area of the triangle, and this equivalent load will pass from the apex at a distance equal to 2L by 3 and from the base it will pass at a distance equal to L by 3. So in this case, the equivalent load is nothing but the area of the triangle. Area of the triangle is same as 1 by 2 into W0 multiplied by L. And this load from the base will act at distance equal to L by 3. So this distance is L by 3. In this case, the maximum bending moment will be at point A and we have maximum bending moment is same as equal to MA is same as equal to 1 by 2 into W0 into L multiplied by distance is L by 3. That is, we have maximum bending moment equal to W0 multiplied by L square. 2 into 3 is same as equal to 6. This time we are knowing the maximum value of a bending moment equal to 9.849 kilonewton meter. So we will substitute here the value of MA, that is maximum bending moment, equal to 9.849 equal to W0. Unit is kilonewton meter. The W0 will come as kilonewton per m and we have value of L is in meter is 3.6. So we have 3.6 square divided by 6. So the load intensity W0 will come out to be 4.56 will be kilo Newton per meter. A structural T-section is used as a cantilever beam to support a triangular distributed load of maximum intensity equal to 600 Newton per meter. That is the value of W0 is given. Concentrated load is also acting at the free end equal to 1 kilonewton. Determine the maximum tensile flexure stress and the maximum compressive flexure stress at end A. You have to calculate both. What is the stress on the top fiber and bottom fiber, and you have given here the cross section is T. For this cross section, That is, we have given the T section here. The centroid from the bottom fiber is 157 and from the top fiber it is 46 mm. And the value of Iz is also given, that is 13.8 into 10 to the power 6 mm to the power 4. Since we are interested to know the bending stress here, first we calculate here what is the bending moment at point A, and then we'll calculate the bending stress. So we'll set our axis system here. Horizontal axis will be Z axis here, and the vertical axis will be the Y axis. So this distance will be taken as positive distance and is Y top. This distance will be taken as negative value because the bottom fiber is below the centroid. So this one is bottom distance, and we'll take this value as a negative value. Since we are interested in the bending moment at point A, we'll convert the UVL into equivalent point load. That is the area of the triangle will be same as equal to W0 multiplied by 2 multiplied by 1 by 2, and that will act at a distance equal to L by 3, where we have L will be equal to 2 meter. So the area of the triangle is same as 1 by 2 intensity equal to W0 multiplied by L, where L is the entire span, and it will act from the point A at a distance equal to L by 3. L by 3 is nothing but the centroid of the triangular section. In addition to that, we have one more load is acting equal to 1 kilonewton at the free end. So at free end, we have load is equal to 1 kilonewton. Since we are using here W equal to 600 Newton per meter, we'll take this load equal to 1000 Newton. So at point A, we'll show here one reaction in a downward direction that equal to VA, and one moment will show in anti-clockwise sense. This value is equal to MA. So we have sum of moment of all forces about point A. Since we have assumed anti-clockwise positive, so we'll take this value as anti-clockwise, and this sum must equal to 0. Anti-clockwise is positive. Bending moment of equivalent point load will be the clockwise will be taken as negative value is minus 1 by 2 multiplied by W0 into L by 3 is L square and divided by 3. Bending moment of 1000 about A is also clockwise, so that will be negative value is 1000 multiplied by L. So we have 1000 multiplied by L, and the value of MA this time is anti-clockwise. Anti-clockwise is positive, is MA must equal to 0. So maximum bending moment in this case will be at fixed end and is equal to MA is equal to, this value will shift to the right is positive, is 1 by 6. W0 is same as equal to 600. L square is same as equal to 2 square. This value also become positive. So we have plus 1000. L is equal to 2. So this maximum value will come out to be is a positive value. Positive value means that the assumption is correct, and this value come out to be 2400 will be Newton meter. So this one is a case of hogging, and whenever we have a hogging, you have to treat the value of M as a negative value. So because of hogging, we have to treat the value of M as a negative value is minus 2400 Newton meter. For Y top, the distance is positive. For bottom, the distance is negative. So we have maximum value of a bending stress at top will be equal to minus of M into Y top divided by moment of inertia Iz. M is same as 2400, that is Newton mm. So you have to multiply this value by 10 to the power 3. But value of M is negative, and negative become positive, so this value become positive value. M is negative, and already we have negative become positive. Y top is same as equal to 46. So we have multiply by 46 divided by the moment of inertia Iz, that equal to 13.8. 13.8 into 10 to the power 6. Solve this value, we will get the value of sigma top. So if you solve this, you will get this answer equal to 8 megapascal. Answer is positive. It means that on the top we have a tensile stress. Similarly, we can use the same formula to calculate the stress on the bottom fiber. Only thing that instead of Y top, we have to replace the Y bottom. That is the YB value. So maximum stress at the bottom fiber is minus m into yb divided by iz. So we have minus. Bending moment is also negative, is 2400, but negative value. So we have minus 2400 into 10 to the power 3, that is Newton mm. This is negative, negative, negative become positive, but we have yb is also negative. It means that resultant value will come out to be negative, divided by iz. Iz is same as 13.8 into 10 to the power 6. Negative, negative, positive, and again negative. So we have a compressive stress at bottom. So solve this, we will get negative value, and we have minus 27.3. That will be the compressive value. So we have on the top fiber, we have tensile stress equal to 8 megapascal, and bottom fiber we have minus 27.3, that is a compressive stress. A cantilever beam of 50 mm wide by 150 mm high and 6 meter long carries a load uniformly from 0 at the free end to 1000 Newton per meter at the wall is same as 1 kilonewton per meter. What is the maximum flexure stress? We have to find out. Since our section is a rectangular, so the distance of the top fiber and bottom fiber is same, that equal to h by 2. So in this case, we have base is equal to 150. We have a height is equal to 150 mm. Horizontal axis is same as our z axis, and the vertical axis is y axis. Both the top fiber and bottom fiber here are equidistant from the neutral axis, which is passing through the centroid. So value of c is same as equal to h by 2. So we have c is equal to h by 2. H by 2 is same as 150 by 2 is equal to 75 mm. The next job is to calculate the value of the maximum bending moment. Maximum bending moment in the case of cantilever is always at point A. For this purpose, you have to convert the UVL into equivalent point load. The equivalent point load is same as the area of the triangle, that equal to W0 multiplied by L divided by 2. And this load from the base act as a distance equal to L by 3. Let here we have shear force at point A will be equal to VA, and let assume that we have bending moment at point A is equal to MA. To find out the bending moment at point A, we'll take the sum of moment of all forces about point A. Anti-clockwise moment will take it positive, and the sum must equal to 0. This moment of W0 into L by 2 is a clockwise is negative, so we have minus W0 into L by 2, and we have distance is L by 3. Whereas the moment of MA we have shown is a positive value, so we have plus MA. This sum must equal to 0. So bending moment at point A is a maximum value is same as equal to W0 into L square divided by 6. We have W0 is same as equal to 1. L square is same as equal to 6 square divided by 2 into 3 equal to 6. So this answer is same as 6 kilo Newton meter. Since we are interested in the maximum bending stress, so we have maximum bending stress is simply given as the maximum value of bending moment, that is value of M max. The distance C, which one is the maximum either of the top or bottom, this time both distances are same, and divided by the moment of inertia equal to Iz. Maximum bending moment here is 6 is kilonewton meter is 6 into 10 to the power 6. Value of C is equal to 75 mm divided by Iz. Iz is BH cube by 12. So we have 50 into 150, and we have to make a cube of it. 12 will shift in numerator. So the maximum value of a bending stress is compression and tension both magnitude wise is 32 megapascal. 32 megapascal. The video you are watching is from the app, which is the Mohod class app available on Google Store, and in this app we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile The link is given here.